Welcome, my dear students and others, to my continuing coverage of Chapter 11's discussion on liquids and intermolecular forces. This was going to be short and sweet, but it is very important. We're going to discuss heat curves. So when ice is heated from negative 25 degrees Celsius at 1 atmosphere, you can see down here, its temperature gradually rises. Now, it stays solid as long as it remains below 0 degrees C. At 0 degrees C, however, the ice starts to melt. Now, because melting is an endothermic process, the ice actually stays or plateaus at 0 degrees Celsius, even as you add more heat energy until all of the solid ice is completely melted. See that no temperature change even as you add more heat? Now, once all of the ice is melted, then it converts completely to liquid, and then after that, adding more heat energy changes its temperature. And now all of the ice is now liquid water. Eventually, as the liquid water's temperature gets increased, it will reach 100 degrees C. Once we hit this 100 degree temperature, all the heat energy that we add goes towards wiggling those water molecules apart and converting them from a liquid to a gas. Thus, the temperature plateaus and remains completely unchanged until all of the liquid molecules have converted to gas. After that has happened, then added heat energy will increase the temperature of the gas itself. This kind of figure that shows the change in temperature as you move a substance from solid to liquid to gas is called a heating curve, or sometimes just a heat curve for short. This takes us to a beautiful example problem. Ethanol melts at negative 114 C and boils at 78. Additionally, its enthalpy of fusion is this number, and its enthalpy of vaporization is this other number. Moreover, the specific heats of solid and liquid ethanol are these two numbers respectively. And with all of this data in mind, how much heat is required to convert 42 grams of ethanol at 35 C all the way up to the vapor phase at 78 C? And separately, how much heat is required to convert the same amount of ethanol at negative 155 C all the way up to the vapor at 78 C? Now, I'm not going to answer these complicated questions for you here, but I have a link in the video description below that will take you to a separate video in which I work it out for you. I strongly invite you to check that out if you want. This takes us to our final problem for this video. If 42 kilojoules of heat is added to a 32-gram sample of liquid methane under 1 atmosphere pressure at a temperature of negative 170, as showcased in this figure right here, taken from our text referenced in the description below, what are the final state and temperature of the methane once the system equilibrates? Assume no heat's lost to surrounding, and that the normal boiling point of methane is this number, and the specific heats of its liquid and gaseous states are these two numbers respectively. Additionally, the delta H, or change in enthalpy of vaporization, is shown over here. Now, similar to the previous problems, I'm not going to do this one here, but I do have a link in the description below, or possibly floating over my head, to a separate video in which I will work them out for you. I strongly advise you to check those out. Until next time, my students and other viewers, please have an enjoyable rest of your day.